All right, so I'm going to introduce today some laws of chemistry. You might have heard of some of these as well already. The law of conservation of mass, for example, telling us that when we have a chemical reaction, the starting materials, which we also call the reactants. So let me write a little chemical reaction down here. If I have this general chemical reaction, A plus B, forming C plus D, all right? This chemical reaction, these are my reactants, A and B, and C and D we call our products, all right? The law of conservation of mass says that the mass of all of the reactants has to equal the mass of all of the products. Because when we do chemistry, we don't create mass or destroy mass, all right? And then we also have something that's called the law of definite proportions. The law of definite proportions, that means that if I have a pile of a given chemical, so for example, if I have a pile of, let's say my sodium chloride that we talked about last time, if I have some sodium chloride here, I know the ratio of my sodium chloride here is a 1-to-1 ratio. Well, if I have another pile over here, but it's a smaller pile, if it's still sodium chloride, then the ratio must also be same, 1-to-1, okay? That's the law of multiple proportions. If I'm dealing with the same material, it has to have the same ratio of the elements. Okay, very good. And here's some examples of the law of the law of conservation of mass, right? And then we can try this kind of an example. If we take magnesium and burn it in the presence of oxygen and form magnesium oxide, then if you take the 16.88 grams of magnesium and combine it with oxygen and create 28 grams of magnesium oxide, the question in this situation here is how much oxygen was consumed? How much oxygen was consumed? All right, and we can answer that. We can know that this is basically a chemical reaction that's occurring. We're combining magnesium with our oxygen gas, and we're creating our magnesium oxide, okay? And when we do that, then we said that we consumed 16.88 grams of magnesium, and we made 28 grams of our magnesium oxide, all right? From this, can we tell how much oxygen we consumed?
Yeah, you can just subtract the 28 or 16.288 from the 28.
So if I take 28 and subtract 16.88, that'll give me my grams of oxygen, and that is because the law of conservation of mass, right?
Yeah.
Okay, very good. The law of definite proportions, right? If I combine two elements the same way every time, I should get the same combination, okay? Here's another example, or here's a problem that we can use to kind of think about the law of definite proportions, all right? In this case here, I have a sample of magnesium oxide, 16.89 grams of it. Here it is, 16.89 grams. This is magnesium oxide, all right? And then I have another sample that only contains 2 grams of magnesium oxide. All right, same material here and here, all right? So can I tell, if I know that in this 16.89 gram sample, if I know that I have 11 grams of oxygen, can I determine how many grams of oxygen I would have here?
Probably. Let's see, the 16.89, that's magnesium oxide, and if 11.11 of that 16.89 is oxygen, then you should be able to use that ratio and find out what amount of the 2 grams of magnesium.
Okay, so 16.89 was grams of what?
It's 16.89 grams of magnesium.
That's right. 16.89 grams of magnesium. So 16.89 grams of magnesium, all right, and 11.11 grams of oxygen. And you're right, like you said, that ratio should still exist for this magnesium oxide over here, even though it's a smaller amount. So I can set that equal to 2 grams of magnesium over here and identify how many grams of oxygen are in my unknown. Do you know how to solve that problem?
Yeah, I can solve that.
What do you do? How do you solve it?
I multiply the 2 times the 11.11 and then divide by the 16.89.
Very good. So this is what they taught me in math class. We call this cross multiplying. You set x times 16.89 equal to 11.11 times your 2 times the 2, right? And so 16.89x equals 22.22, and then we divide both sides by 16.89. Okay, so x will equal our 22 divided by our 6.89, which is 1.32. Okay, very good. So, as we talked about, everything in the universe is made up of atoms. Everything is made up of atoms. And this is kind of what we call our atomic theory, meaning the atom is the smallest thing, and we can't break apart the atom. And that's true for chemistry class. We've learned a lot over the years, and we understand that atoms actually do break down, especially large ones, and smaller ones can come together to form medium-sized ones, right? But in general, in chemistry class, we don't break down atoms. Atoms are the smallest component of matter. Okay? The law of multiple proportions combines atoms, but the combination can occur in different ways sometimes. All right? So we just said that the law of definite proportions showed that atoms will combine the same way, but that's if you combine them the same, or you mix them the same way every time. If you perform the chemistry differently, at different pressures or under different conditions, temperatures, then you can get different products forming. Okay? So this we call the law of multiple proportions, basically showing that it is possible to combine elements some ways and form different compounds. Now, we talked a little bit already about chemical reactions, but we want to finish this conversation up about that. We have our reactants on the left, we have our products on the right, and I've used some chemical reactions so far, and I didn't take the time to what we call balance the chemical reactions, right? But we want to make sure that we recognize that the number of elements of hydrogen, chlorine, calcium, carbon, oxygen on the left of this chemical reaction are going to be the same number of elements of the same elements on the right side of the reaction, right? We don't create elements, we don't destroy elements, right? So we can balance these chemical equations by changing what we call the coefficients. The coefficients are the numbers in front of these different compounds, all right? We can't balance this equation by changing the small numbers down here, the subscripts, because that would be different chemistry. We're changing what's actually happening in the chemical reaction. It's a different chemical reaction altogether. If we're given a chemical reaction like this one here, and we need to balance it, all we can do is change our numbers in front, the coefficients, all right? One more thing. Do you know what this little S stands for?
That means solid.
Very good. Do you know what this L stands for?
That's liquid.
And G?
Gas.
Right. So we have different states, we call those. Solid, liquid, gas. If I take a solid and convert it to liquid, that's melting. Take a liquid and convert it to gas, that's a evaporation, all right? I should write that out because I don't want to confuse you. You never change water, for example, from a solid to water that's a liquid. That is melting, right? You can see that that's not a chemical change, is it? It's a physical change. The atoms, oxygen and hydrogen, are not